In this lab, we are going to continue looking at the modern digital design flow, but now we're going to build a much larger circuit, which is going to be a 7-segment display decoder. But this time we're going to have 4 inputs, and this creates a very, very large circuit because now what you're going to have to drive the display decoder is you'll have 7 unique 4-input combination logic circuits. So this is something that would be very, very difficult to breadboard with discrete parts. It would take a lot of area, a lot of time. It would be very prone to errors. So this is where you start seeing a circuit that is large enough that you really start needing to move to the modern digital design flow. So in this exercise, what we're going to do is we're going to build this in VHDL, and we will then synthesize it, put it on our FPGA, and we will interface it to the 7-segment display decoder, or 7-segment display that's on our breadboard from a prior lab, and then we'll test it. Okay, so the learning outcomes, the first thing that we're going to learn how to do is we're going to create a new Quartus project, but we are going to copy a prior Quartus project. So this is a real common way to do things. It's called design reuse. So if you recall, in lab 5.1 we built a prime number detector, and we went through and selected the device and we assigned pins. This time we want to leverage all of that work that we did, and so we want to create a copy of that project and make it this new 6.1 lab. And then what we're going to do is we'll go in and modify it to add the functionality for the 7-segment decoder. And then we'll actually, of course, one of the outcomes is going to be we'll create a 7-segment decoder in VHDL. Okay, so here's what you need. You need your breadboard and wires. You need your LED driver circuit from prior labs. Okay, and then you're going to need your buzzer, of course, 7-segment display, FPGA board and USB cable, and now you're going to need 10 female-to-female jumper wires. Okay, so what we are going to actually do here is we will keep the 7-segment display on the breadboard, all right, and then we will drive it from the switches, the slider switches on the FPGA board. Okay, and all we're going to do is just demonstrate the entire thing, and then so that's 90% of the exercise, and then 10% is just delivering the top.VHD. But we also want to keep our prime number detector, because wouldn't it be neat if every time the display showed a prime number, it also asserted the LED that we've been driving this whole time and turned the buzzer on? So we want those to also be there. So here is what the block diagram is going to look like. So on the left, of course, is our FPGA board, and the 4 inputs are going to come from the slider switches. We're going to route those back to the LEDs on the FPGA board so that we can see what the inputs are. And now what we're going to have is we're going to have 2 circuits on the FPGA. We're going to have a 7-segment decoder, which is going to produce 7 outputs, which will then bring over to the GPIO1 connector, and will jumper the 7 wires over to the 7-segment display. Okay, and you still need the 150 ohm resistors in series with them, but those should be on your breadboard from lab, one of the prior labs. But then we also want prime. Okay, and so we're going to move prime down to pin 18 just to make it a little bit easier to lay it out on your breadboard. And so that's not a big deal. We just change the pin assignment. And we'll jumper that over to the normal LED and the buzzer, just like normal. And then what's going to happen is we need power and ground in order to interface these two. So we're going to have ground again from pin 30, and then power from pin 30 or 29, which is bringing in 3.4 volts. Here is a picture of what your system is going to look like. Okay, so we're going to have the inputs over here displayed on those LEDs. We will have the 7 segments, 7 signals coming from the decoder over here. And what I did is I have my 7-segment decoder right here. Resistors come up, and then I jumper wire them over to get closer so that I could actually kind of jumper twice. And right here you're going to see 7 these little 1/10" header pins. So I got 7 of them placed there. Prime comes down here. It comes over to this to drive this LED, and then of course picks up the buzzer. Okay, so here we go. First thing we need to do is design the 7-segment decoder logic. Now, you've done one of these in the past. You did this on lab 4.3, but that only had 3 inputs. So we really only had the characters from 0 up to 7. This time we're going to go 0 all the way up to 15. 0, 0, 0, 0 up to 1, 1, 1, 1. And so we're going to have 16 unique symbols. So what do we do after we get to 9 and go to decimal 10? we'll just put the hex symbols. So we'll have a capital A, lowercase b, lowercase c, lowercase d, capital E, capital F. And that's just kind of a common way that you do the 7-segment decoder symbols. So the first thing we need to do is we're going to implement this, but we need to know what the ones and zeros are. So to do this, we are going to have a 7-bit output vector in our FPGA design, our VHDL, and it's going to be called 7seg. And what we'll do is we'll have the most significant bit be LED A in the display, and the least significant be LED G. And all we need to do is put in the ones and zeros in order to get the corresponding character. Okay, so I gave you the first one. It's like if you have 0, 0, 0, 0, you're going to need 1, 1, 1, 1, 1, 1, 0. So that means you're lighting up all the outside LEDs and not G. So you first have to fill this table in so that you know what functionality you're actually even trying to get. So that's step one. So go ahead and do that. And now we're ready to fire up Quartus, and we are going to open up the last project, 5.1, and we're going to copy it. So that will preserve all of the work that we did in order to set up the project and create the device. So go ahead and fire up Quartus. And so here comes the Quartus screen right here. And this is a blank project. And I am going to open Lab 5.1. So I'm going to go Open Project. And I'm going to come, here's Logic Lab, my main folder. And here's this Lab 5.1. I come over here, and this QPF file is the project file. Okay? And luckily I named it descriptively last time, so I have lab 05P1 prime number detect, and I go ahead and open that project. Okay, so Quartus is going to work for a second while it opens that up, and then what I'm going to do is I'm going to copy it. And the copy tool within Quartus is really nice because we want to keep all of our projects organized, and that's why we created this Logic Lab folder. Okay, so we have this Logic Lab folder, and then last time we had to manually make a folder for a new project. Well, this time we don't need to do that. It'll allow us to create that folder automatically. So now this is open, and I'm going to go Project, Copy Project. Now the Copy Project screen comes up, and at this point what we want to do is we want to give it two things: the destination directory and the project name. And so now you're going to type in the destination directory because this is going to be created. Okay, so what I want to do is I'm going to use this right here. I'm going to use this file name. It's going to be called Lab 6.1 7seg decoder. Okay, so let's 7seg decoder. So I'm going to call this 06P1, and then I'm going to call it 7seg decoder. Now that is the folder. It is going to create that folder for me, but I also want to change the project name. So I'm going to make them identical, just like we did last time. Now the top level entity, it's not asking for it because it already exists in Lab 5.1. So go ahead and keep Open New Project checked. Say OK. Do you want to create this? Absolutely. That is absolutely what I want to do. So it creates it, it goes ahead and opens it, it closes Lab 5.1, and now I'm sitting here where once it gets done spinning, you have a new Quartus project, which is 6.1, and this is the new 7-segment display. Okay, so this is great. If I go into Windows Explorer and look, I have now created this folder, and everything is nice and clean. So every folder represents a new project. This is almost always how you're going to do it because it's just great to start with something that already works. Okay, so I can come over here and I can click on top.vhd, and I see everything from last time. So at this point, I could potentially download last Lab 5.1, but I don't want to do that because I want to get going with the new 7-segment decoder. So let's first think about the ports. Okay, so let me pull up the handout here, and I want to think about what ports we're going to have. We are going to have the same ports: SW for the switches, 4-bit vector; LEDR, 4-bit vector for the red LEDs; prime, of course, but we're also going to add a new one, and it's going to be called 7seg, and it's going to be a 7-bit vector. And this is going to be an output vector, and these will be the 7 outputs of the character decoder. So we need to add that in there before we actually add the functionality. So here's what I'm going to do. I'm going to go ahead and come into here. Let me get this so you can see everything. Okay. So now what I'm going to do is I'm going to come into the entity, and all I'm going to do is add this new port. So 7seg, and I'm going to make it an out, and it's going to be a bit vector, and it's 6 down to 0. All right, so I just did that, put a semicolon on that, everything's great, Let's go ahead and line these up a little bit. Okay, so I have it. I have everything's great in here, and I'm going to save this up. I need to compile this first. The reason I need to compile it is I need to have Pin Planner reflect that I have added 7 new pins to my design. So the first thing I'm going to do, I'm going to keep all of this. I'm going to keep my prime number detector and my switches driving the LEDs. I want that there, but I want to compile the design, and it'll say, well, you've already done it. Well, it's got to do it again. So go ahead and force it to redo it again. That will force the new port to show up in Pin Planner. Okay, so let's let this run for a second. Okay, so I have successfully compiled and synthesized, and I actually had an error in there. I actually had I was missing one of these closed parentheses, so I had an error that showed up down there, and I fixed it and recompiled. And so now it's all successful. And I did that first in order to get the Pin Planner to reflect these new pins. So when I come in here, what I'll notice is that I have this new vector called 7seg, and it's got 7 bits in it, and they're all outputs, but they don't have pins. Okay? All right, so now what we need to do is we need to figure out which pins are pins, which pins are what. And I already did it for you. I went out to the user's manual and I said, okay, I want to move prime. First of all, I want to move it down a little bit so that it's easier to jump her over. So I want that to move to pin J11. And then here's the pins that I'm going to assign for 7 segment, bits 6 through 0. Okay. So the first thing you have to do is you're going to want to move. You want to move prime from A12 to J12. And then we go ahead. Didn't like J12, but I got J11 in there. Okay. So let's see. I don't want that on 7 segment. That's what I want for prime. So here's, I clicked the location and sorted them that way. Let me get it back to node name. Okay, so now this now is, I want it on J11. Okay. And now I want to go to 7 segment and I want to put this on pin underscore A12. And then I'm going to do this on B12, and then I want to do this one on B13, and then I want to do this one on D13, and then I want to do this one on G17, and I'll do this one on J18, and you can tell that this is where most designs are messed up, okay, because it's you spell something wrong in here, you get the wrong number in here, and then the pin isn't routed to the right pin, or the signal isn't routed to the right pin. But let me check these really quick. So I'm going to go from 7seg 6 down to 0. So it's A12, B12, B13, D13, G17, J18, G11, and then prime move to J11. Okay, and so if you're like, where are these pins coming from? I mean, so the pins, I went into the user's manual and I figured out what the pins were for. Let me show you this block diagram. I figured out what the pins were for this connector. So I wanted pin 2, 4, 6, 8, and I chose them so that it was 7 in a row that I could jump her directly over to my breadboard. And then I moved prime down here just so it was a little bit lower because my LED driver is down there. Okay, so now I have this, and again, everything looks fine, so I'm going to go ahead and say File, Close, and I need to recompile again. So go ahead and double click on, actually, you know what, we don't need to recompile right now, we can, but we can also go ahead and add in the functionality for the 7 segment decoder. Okay, so now let's take a look at how we might do this. We already have the logic that we want from our table, and what we're looking at is we really want the decoder written in VHDL. So here's a couple examples again. So I'll get you started here. We are going to assign to the vector 7seg, but what's so great about VHDL is you can assign a 7-bit vector directly to it. So for example, when the switch is equal to 0, 0, 0, 0, you can assign it 1, 1, 1, 1, 1, 1, 1, 0. Okay, that was the same row of the truth table that I just filled out. Okay, and then for 0, 0, 0, 1, I assign these bits to 7seg in order to get the 1 character display. And I need to fill that out. I need to have 16 of these assignments in order to implement the 4 bit input of this new decoder. That's a conditional signal assignment. You can do the exact same thing with selected signal assignment. Same functionality, it's just a little bit slightly different syntax. So you do whatever you want, but when you do this, don't delete the switches to the LEDs. We want that. And also don't delete the prime number detector. Okay, so that was important from last time. So you can come down here and you can write the code, so you can say, put up some comments, and I'm going to enter my code right here. Now, I did this earlier, so let me go ahead and paste mine in, and then we'll compile. So look at that. I got all my assignments in there. It feels so good. Okay, so now I'm going to go ahead and save it, and now I want to compile design, and off it goes. So now let's wait a second while this compiles. Okay, so when I compiled that, I had a whole bunch of errors, and so it's complaining because it doesn't allow 7seg. It's not able to drive the 2.5 logic I/O standard, which is good. I'm glad it told me that because I actually forgot a step in here. So if I go back to Pin Planner, one of the things I forgot to do was I assigned its direction, which was great, but I didn't assign its logic level. So remember how prime we assigned it the 3.3 volt CMOS? I need to do that since these signals are going over to my breadboard. I need to do that for each of these guys. So I forgot to do that, and luckily I got a big old error on it. So let's go ahead and change all these to 3.3 volt CMOS. So 3.3 volt CMOS, and then 3.3 volt CMOS. And then I also, while I'm doing this, I want to also change the drive strength so that it can drive enough current to light up our LEDs on our 7-segment decoder, or 7-segment display. Okay, so here we go. One more to go. All right, so now let's see. Let's check these. I've got all of my outputs that are going over to the breadboard to be 3.3 volt CMOS, and then I need to come to my over here, and I want to go maximum current for all these, just so that it's not limited in that. That's wrong there. I clicked on the wrong one. That's 3.3 volt CMOS. Okay. Like I say, Pin Planner is where a lot of errors come from, so it's like, take your time, but it's also one of the first places when you get an error. Not so much even an error is when your design doesn't work. It's like you don't even know where to start. I always start with Pin Planner. Okay, so let me check this. So 3.3 volt CMOS, LV CMOS, maximum current. This looks very much better. Okay, so I got that in there. Let's try this again. I'm going to close that. It takes it. So I go ahead and compile design, and let's see if this runs now. Let's let it work for a second. Okay, so that worked there. Okay, so this is great. I've got my entire thing entered, okay, and I'm ready to, in no errors, and it's synthesized great. So I'm going to go ahead and fire up Program Device. Version 17 of Quartus will go out and automatically find, the device. And now I'm sitting here, and it has this, and so I'm ready to, it says no hardware, so I'm going to go ahead and oh, I'm sorry. We need to connect the board, okay? So I bring up this. The reason it's not finding any hardware is because I don't have the FPGA board on yet. So let's go ahead and come out here, and here I need to make my connections to the breadboard. So what I'm going to do is notice that, again, I've got my power and ground, which I take from these pins right here, 29 and 30. Bring them over, put them in the rails of my breadboard. Here's prime. I've moved prime down to be this pin right here. And then I have my 7 pins in a row right here. Something important to keep it note, when you look at the block diagram, there's 5 pins in a row, and then there's a gap, and then there's 3 pins in a row. Okay, so make sure you don't have that. Make sure you have that gap. And then what I did is I brought over these guys, and I put 7 little pin headers that went into the breadboard, and then I jumper them over to here. And then here comes prime, and I go ahead and jumper that up to the buzzer. Okay, so now I'm ready to make sure that I can turn this on. So I turn it on and give it a second, and okay, so it runs its normal program again. And nothing's on the FPGA that I designed, but I do have power coming over my breadboard. So I want to make sure that I got power. I turn on my LED. It's like, this is fantastic. I know that I have power and ground, so at least I have a chance of making this work. Now I'm ready to go back to my programmer. And this time, if I have no hardware, I can come into here and say USB Blaster. Now, that was very important to do because when I opened Programmer, it didn't see this board. It didn't go out and automatically detect it because I didn't have it on. Okay, so let's go ahead and start this thing up. and while it's programming, the buzzer goes on for some reason. I can unconnect that, but it's kind of cool actually. Okay, look at this. Look at this. I have a 0 being displayed on my character display. So let's go ahead and see what happens if I change this to 1. Oh, look at that. So now I have 1. Here comes the big dog here, because I'm going to go to 2, and it should be a prime number. And so I go, and look at what happens. The LED lit up, indicating it is a prime number. It displayed 2, and the buzzer went off. Okay? And now let's go to 3. Perfect. And now here's 4, no prime number. 5's a prime, 6 is not, 7's a prime, 8 is not, 9 is not, 10 is not, 11 is, but 11 displayed in hex is a B. And then we go to 12, 13 is, 14, 15. And I cycle through all my characters on here. Okay, so that's the deliverable. Quick video, try to buzz through those 2-3 seconds. That's a deliverable for 90% of this exercise. And then go ahead and you got to grab your top.v and provide that, and that's the deliverable number 2. Let me give you a hint on debugging. One of the things that I always run into is you'll put this design over here, and like one of your characters won't be on. Okay, so like you test 0, and one of them's always off. Okay, so what happens is it's easy to flip through these and figure out which one it is. It'll always be the same LED. So what I do is I always start by saying, okay, so if I have this one LED that's out, let me just pull one and see. Let me give you an example. So let's say that this LED is always out. What I'll do is I'm trying to isolate what's wrong with it. And so I want to know, was it something on the FPGA side, or was it something over here? So what I'll always start with is I'll take the wire that is driving this, and I'll actually just plug it right into the power supply. And I can do that and turn it on and off. And if I do that, it tells me that I have the path from VCC through the resistor, through the LED into ground working, and I can isolate that. And then when I plug it into here, that allows me to say, okay, wait a minute, the problem must be over here. So then I start going over here and I start debugging the FPGA. And like I say, I always start with pin planner. I always go and verify that I have the right pin assignments and the right logic level, the current, etc. If the pin planner is okay, then I actually go back and then I look at my VHDL. Okay, and then the VHDL, make sure that that's okay. Okay, and then if that doesn't work, you actually go back through every step of the design flow and make sure that it worked. So you did it. So now let's see if you were able to do this lab, which I hope you did. Could you answer these? Could you take advantage of design reuse by creating a new project by copying a prior design in Quartus? Hope so, because that's what we did. And the whole purpose of this was that you don't start a project from scratch very much. Okay, we had to do it one time, but from here on out, you usually if you're always targeting the same board, you always copy what you've already done, and it just saves you time. And then the other thing is, could you use concurrent signal assignments? Concurrent signal modeling techniques to create a 7-segment decoder design in VHDL and implement it. Well, if you got the demo to work, you absolutely did that. The point here, though, is really powerful because this is the first circuit we've looked at it's just flat out too big to implement it in discrete logic practically. You could probably do it. You might even be able to fit it on one breadboard, but you get to the point where you just got so many wires going every which way where you say this is taking a long time, it's very error prone. I need to move from the classical digital design approach to the modern digital design approach, which is where you use an HDL and a synthesizer in order to automatically create the logic for you. And that was the whole purpose of this lab. So if you did it, congratulations, and we are done.